All right, we are in 12.5, day one. We're going to do this one in 2 days. Equations of lines and planes. So first thing we're going to do is we are going to get rid of this. There is no ebook homework assignment. It's just your web assignment. All right, so we're going to define lines and planes in both 2 and 3-dimensional space. Fortunately, we kind of know what lines are in 2-dimensional space. We've been dealing with those since Algebra 1. In 2-dimensional space, we know that any 2 points create a line. So all you need are 2 points. However, to write the equation of a line, we know the most important thing that we really need is the slope of the line. And then any other point. So if you have the slope, any point, you can write the equation of a line. In 3-dimensional space, the same criteria is going to hold true, but the point now needs to be accompanied by something with direction. Specifically, we need to have a parallel vector. So this is the way we're going to go about writing the equation of a line in 3-dimensional space. We've got 2 points in 3-dimensional space, x, y's, and z's. What we need is we need a starting point, and then we need to figure out how it changes in the x, y, and z directions. So we can pick either point. In this case, we're just going to go with the first one here. We're going to call this one our starting point. And basically, we need to know how x, y, and z change. Well, the x part starts at 1, and it changes by 1. It goes from 1 to 2. So it changes by 1. So it's going to be plus 1 t, or just plus t. And then the y part starts at 4, and then it looks like it goes up 3. So every time, again, it's linear, so every time it should change by the same amount. So the slope between that is going to be 3t, or the slope is 3, multiplying it by the t. And then the z part starts at 3 and goes to 10, so it changes by 7. So each one of these things is written in what would normally look like your standard y equals mx plus b type form. This is what is called the parametric form of a line. We had to do it parametrically. Parametric form of a line. And the reason for that is we can't just write something in, like in 2 dimensions, y and x is y equals mx plus b. As soon as we throw the z in there, it no longer is a line. It becomes a plane, which we will deal with later on in this section. So once again, what you need to write the equation of a line is you need a starting point, and the changes in x, y, and z. Those are the things we're going to need. Okay. Otherwise, it is pretty much the same idea. Change of y, change of z. Change of x, change of y, change of z. And so it says here, let's look at this at WinPlot. That was actually back when I used to use WinPlot. If we have time at the end, we'll actually look at this in CalcPlot 3D. We'll see if we have time at the very end of the videos. All right. There are 3 forms of every line. The one we just did was called parametric. The other 2 are called vector and symmetric equations. Okay, vector equations are actually really simple. The vector equations are really just, or the vector form, excuse me, the vector form is really just going to be the parametric form written as a vector. So from the previous example, or no, from this example, I'm sorry, if I was going to write this Okay, no wonder everything was looking a little bit weird here. My stuff got shifted a little bit, so I'm going to write this in between here. The vector form, for some reason that example 2 got shifted up for me. Vector form, again, it's just going to be taking the previous one, which I'm going to scroll back up here, and writing it in vector. So it's 1 plus t, and then 4 plus 3t, and then 3 plus 7t. And that's because the first component is x, second component is y, third component is z. The symmetric form, which is the last one, involves just a little bit of work. It's not horrible, but it does involve a little bit of work. The symmetric form basically just says we need to solve each one of those pieces for t. So if I go back to the parametric form up there in green, and I solve that for t, I would have to subtract 1 on both sides, and then I would be done. So I'll have x minus 1. If I solve the y part for t, you would subtract 4 and then divide by 3. So you would get that that equals y minus 4 all over 3. And then if you do the t part, the z part, it's going to be z minus 3 divided by 7. Z minus 3 divided by 7. And it's called symmetric form because we just literally solved the parametrics, every one of them for t. So if that's the case, all 3 of those things are equal to each other because they're all equivalent to t. Okay, symmetric form is not really heavily used, but vector form and parametric we will use quite frequently. So basically in symmetric form, again, the thing you're supposed to do here is solve for t, and then set them all equal to each other. All right, now let's see how we're going to work this thing here. Find the equation of the line through those points. I think I've got enough room to do this on here. Again, I don't know why it shifted, but we'll deal with it. All right, so if I want to find and we'll just put this in parametric. So x starts at 1 and increases by 1, so plus t. Y starts at 5, and it looks like it goes down by 3 from 5 to 2, so that's minus 3t. And then z starts at 6 and goes down by 4, so that's going to be a minus 4t. That's it. That's all you have to do. All right, let's move on to number 3. Yeah, there was a lot of space on that next page. All right, find the equation of the line through the point 2, 6, 4 and parallel to the vector 4, 1, negative 6. Okay, so this right here is a vector that actually indicates, since our point is 2, 6, 4 and it has to be parallel to that, those pieces right there are really your deltas. Those are your changes right there, 4, 1, and negative 6. That's your vector. So in this case, x is going to start at 2, and it's already telling you it's changing by 4 because that's what the vector does. Remember, the vector already has direction and magnitude. The direction part is the slope. So the fact that it's telling us the 4 there and the x component of the vector is telling us it's changed. It's telling us the slope changes by 4. The y part is going to start at 6 and then increase by 1, so 6 plus t. And then the z part is going to start at 4, and it looks like it's going to change by negative 6 and minus 6t. And that's it. That's all there is to it. And obviously we could put these in other forms, but it doesn't say to, so let's not worry about it. All right, now we got to do a little bit of work. Example number 4, find the equation of the line that goes through the points 2, 1, 0 and is perpendicular to both the vectors 3, 1, 1 and 2, 0, 1. Okay, so if I want a vector which is perpendicular to 2 vectors, we know that that's going to involve the cross product. So we're going to set up a cross product here. I, J, K, 3, 1, 1, 2, 0, 1, and we're going to perform the cross product because now we'll get a vector which is perpendicular to both of these, and then we'll have that vector, we'll have a point. It'll be really simple to write the equation of our line. Okay, so let's go ahead and work this out. Eliminating the I row and column is going to give you 1 minus 0, so that's 1, so you get 1I. Eliminating the j row and column, you're going to get 3 minus 2, so that's 1, but remember it's always minus j. And then eliminating the k row and column is going to give you 0 minus 2, so that'll be minus 2k. So the vector that we need is 1, negative 1, negative 2. That vector is parallel to the desired line. And since it's parallel to the desired line, the 1, negative 1, and negative 2 are your slopes. So all we have to do is pick our starting point, which we have. So x is going to be 2 plus t, because the change in x is 1, given our vector. Y is going to be 1 and minus t. And then z starts at 0, so I don't have to write 0. You can, but it's just going to equal negative 2t. And again, that's it. Writing the equations of lines is not really that challenging to do. Okay. I know that there's a bunch of space on the next page, so I am going to extend my page. I don't know how yours printed, but I'm just going to extend mine here so I don't have to move this down to the next page. It says find the equation of the line through the points 5, 3, 0 and 5, negative 4, 9. And you might be saying, Mr. McCoy, I get this already. This isn't that hard. Let's move on. There is a reason I want to do this one. So let's write this in all three forms. So first of all, let's start off with parametric. Okay, that's usually the easiest one to start with. All right, so we can pick either point to start with. It doesn't matter. I'm just going to pick the first one to start with. That'll be my first value. So it looks like x starts with 5 and doesn't change. So there's 0t. I don't have to write the plus 0t. Y starts with 3 and goes to negative 4, so that's subtracting 7, so minus 7t. And then z starts with 0, so I don't have to write that, and changes by 9, so that's 9t. Writing this in vector form, that's pretty simple. It's just 5, 3 minus 7t, 9t. Not a big challenge there. Now let's write this in symmetric. So here's where the issue lies. I don't have anything to solve for t in x, but we can solve for t in the y part and the z part. So if I solve for t in the y part, I'll subtract 3 on both sides and then divide by negative 7. So you would get y minus 3 over negative 7. And then in the z part, you're just dividing by 9. So that equals z divided by 9. The problem is the x part. Can't solve for t. There's no t in there to solve. So the only way you can write this, and this is kind of seems like cheating, although it's not, is you just write comma x equals 5. Okay, you can't set it equal to the other ones because there's no t value to have it be equal to. So it's just x equals 5 off to the side. So that's your symmetric one. And that's really the only reason I wanted to show that example. All right, this next example, or this next concept, it's a little bit different. So there's going to be 3 types of lines. Lines can be intersecting, they can be parallel, or they can be what's called skew. So the first two we're used to seeing in two-dimensional space. We've done that before. So actually, we can actually sketch that. So in two-dimensional space, you can have 2 lines which are intersecting. Okay, you just have a line going like this, and then some other line maybe going like that or something like that. 2 intersecting lines, no problem. We've seen that before. In two-dimensional space, we can also have 2 lines which are parallel. So again, you have a line which goes like that, and then another line. Whoops, did not mean to draw it in that. Another line which goes something like that, and those two lines are parallel. In three-dimensional space, however, is the only way you can find the last one, because the only other thing that you could have in two-dimensional space is the two lines on top of each other, which means that they would be consistent lines, or they would be exactly the same equation. So in three-dimensional space, however, is how we can have the third one. And this is going to take a little bit of imagination. Hopefully you can understand how this works. So there's our three-dimensional plane. What we could have is, and I'm going to try my best to do this, we could have a line which is like this. So think of that as being someplace up in like the first octant. And then we could have another line which never intersects this one, but it's also not parallel because it's not going to go in the same direction. So maybe this one is in the, like, whatever's below the first octant. So it's going to go over here, and then I'm going to dash it because it's going to go underneath of the y-axis, and then underneath of that line right there, and go off in that direction. So these two lines may never actually touch each other, but they're also not going to be parallel because they do not have the same direction. So that is called skew. The best thing I can tell you to do is take two pencils, put them so that they're parallel, and then take one of your pencils and just rotate it, not moving the location, just rotate it a little bit, and you can see how in three-dimensional space, the two pencils, one of them would be pointing in a different direction than the other one, but they'll still never touch each other. Again, hopefully you can see that visually because that's kind of an important concept. But that one is called skew. So I'll go ahead and write that right here. We'll call that one skew. The other two should make sense, intersecting and parallel. All right, so those are the three different types of lines that you can have. So in our our sixth example, wow, I got ahead of myself. On our sixth example, we want to determine if the lines L1 and L2 are intersecting, parallel, or skew. And we're going to be given the lines in, it looks like, both parametric form. So we're given the first line, X, Y, and Z in terms of T. The second line, X, Y, and Z in terms of S. So here's what we're going to do. We're going to go ahead and check for, intersecting. So if we're going to check for intersecting, that's actually pretty easy to do. So let's start off with the fact that the first one, X is negative 6t, and in the second one, X is 1 plus 2s, so they have to equal each other in order for this to work. So we can actually solve this for t really simply. Divide both sides by negative 6. Now, multiple ways you could go about doing this one, but since I now know the t value, in order for these two things to be intersecting, if I plug that t value back into both of the y's, they better simplify to the same thing. So let's see if that happens. So now we're going to go with y. And let's see. The y on the left-hand side is 1 plus 9t. So I'm going to do 1 plus 9 times 1 plus 2s divided by negative 6. That better equal the y value on the other side, which is already in terms of s, so I don't need to change anything there. 4 minus 3s. These things have to simplify. So let's go ahead and check it out. Here we're going to have 1 plus, if we multiply this thing out, that's going to give us, what is that? So I'm going to kind of try and do this all in my head. If I distribute the 9, I'm going to get 9 over negative 6, which is negative 3 halves. So let's do minus 3 halves. And then 18 over negative 6 is minus 3. So minus 3s equals 4 minus 3s. So if I add 3s to both sides, those are gone. What does this simplify to? 1 minus 3 halves, 1 minus 1 1/2 is 1/2, equals 4. Well, that's not a true statement. Okay, I had to have gotten a true statement in order for these two lines to be intersecting. That's not a true statement, so we know that these are not intersecting. Okay, they must have the same x, y, and z at the same t value. So that has to happen. And in this case, it did not. So let's check to see whether they're parallel or not. So let's check parallel. Parallel is actually much easier to check because what you're looking for is really, do they have the same rate of change? So if we look at line 1, we know what the rate of change is because that comes from the part that's multiplied by the t. So line 1 has the vector -6, 9, -3. Line 2 has the vector 2, -3, 1. And you might look at that and say, well, they're not the same, but technically they are. Because in order for two things to be parallel, they have to be scalar multiples of each other. And in this case, L1 and L2 are scalar multiples. Scalar multiples. Because basically what that means is I could take one vector, multiply it by a scalar, and I'm going to get the other vector. So really it means that they're exactly the same direction. One of them in this case has a slightly different length to it, but they are exactly in the same direction, so they are parallel. And you would know because if you multiply L2 by -3, you get L1. So since that is the case, since both vectors are parallel, both vectors are parallel, the lines are parallel. And obviously we didn't get the skew part, but that's the only other possibility. So if you check them and the lines are not intersecting and they're not parallel, they have to be skew. So you really check the first two to see whether they're skew. There is no actual way to check other than eliminating the first couple of things. All right, that's enough for video 1. We're going to come back and we'll talk about planes in video 2.